you can actually find a closed form formula for the coefficients.
Okay.
So that is this x times x transpose inverse times x transpose times y.
Right.
So that gives, but in when you have large data sets, that's matrix X. The number of rows in that is fairly large. So if you have lots of variables and lots of data, then inverting this matrix becomes pretty difficult to handle. But for small ones, you can do it. I mean, that's.
Right.
Yeah.
So I think that when people do optimized, linear models for really, as Neil was saying, for lots of variables, as said, part of it is you have x transpose or whatever inverse.
Right.
So the inverse, how do you do that?
Yeah.
So when you do that, frequently people will use gradient descent to approximately compute the inverse, or at least to find the determinant. So you can actually wind up using gradient descent in linear models in that way. I mean, there is a closed form solution, but I'm told that for huge systems of linear equations, and obviously there's an exact solution, but people use gradient descent to solve them. It's just faster.
Yeah.
So there's a possibility that when we say that matrix is singular and it cannot be inverted, we can still use gradient descent to find coefficients and still do linear regression.
Yeah, you can. I mean, as we saw, it's a matter of sometimes they don't converge, but in the linear regression, I mean, it can happen. Yeah, it can happen that if there are variables that are very highly correlated or multiples of each other, so that matrix will become singular, and then you can't invert it. But I don't know if. I honestly don't know what you get if you do that. If you get anything useful.
Okay. Yeah. So when we get to when we talk about that linear regression, as you mentioned, like about the correlated variables can make the matrix singular and inversion difficult. That is one question I have. It's kind of a practical question. Like you have 100 variables. Let's say 100 variables in a regression, and now a priori you have no idea which of these variables are correlated.
Right.
Now, what is the best method to make these, to come up with you can do PCA probably, but other than PCA, what can be other way of reducing the number of variables so that you have independent predictors and then do regression on that? There seems to be no simple method.
Well, stay tuned for this lecture.
Okay, all right, so let's start.
You can definitely do some. I mean, there are tricks where you can make if you use regularization, then you can make the matrix invertible. But then regularization can also tell you which variables you can that you can throw out or even that become zero when you do the regularization.
Okay.
Depending on what kind of regularization.
Yeah, right.
Yeah.
So I think Adam will talk about the lasso.
Okay.
But just to give an advertisement, one of the problems is if you have highly correlated variables, that means your matrix is invertible, but the determinant is really small. And so you have to get this inverse. And the inverse of a very small number is a very large number. Right. So very, very small errors in your or differences in your observations can lead to very large differences in what your actual coefficients are, which is very unstable. I mean, if I have a data set that's 1, 1.1, 1.2, and I get out a coefficient of 3, and then I have 1, 1.1, 1.21, and I get a coefficient of 1,000,000, that's that kind of numerical instability is no good. And one of the things regularization will do is it'll force it absolutely will force the coefficients not to be too large. So regularization is the way to deal with these things.
Okay,
and
so I think
will actually even go so far as to say get rid of these variables.
Okay, so I think this will be very interesting because I know of lasso and ridge, but I'll see like how exactly it can be used to get around this problem.
Yeah, it makes the matrices invertible. That's the.
But first,
we will talk about something else.
Okay.
Share your screen.
Or we'll talk about. We should share the screen. All right, is it viewable?
Yes.
Okay, very good. Yeah, so we talked a little bit about regularization last time, not very much, but a little bit. So we were going to go more into depth in this lecture here. So it's as we had just been talking about, it will help you when you have variables or columns that are very highly correlated, and when you get matrices that are singular. But it's in machine learning, it's mostly a tool to avoid overfitting by putting some restrictions on the parameters that you find when you do optimization in machine learning. And it's also necessary just to get convergence in our descent sequences. So we've seen gradient descent, and that does not always converge. And here's a very simple example of that. So we're going to do. We have a data set here with two data points. It's a two-dimensional data points, -1, and 1, and labels -1 and label +1. So I could make a quiz here. Think, what do you think is the line that separates these data sets into the label -1 and label +1s? And you probably would be able to answer that. So I'm not going to post it as a quiz. But how would we do that? Suppose we couldn't figure out how to do that sort of by just eyeballing it. We want to do a logistic regression. So we would have to write up our logistic regression loss function, and that is what we defined last time here. So the logistic regression loss function, when we have a labeled data set, so this is a general framework here. We have a labeled data set. We have data points, data vectors xi, and we have their labels yi, and yi in the logistic regression case is plus or minus 1. And then we had defined this loss function. There's a missing 1 over n here.
1 over n.
We had the loss function here is given by this somewhat strange expression here. We had this logistic function that you remember as 1 over 1 plus x per minus z. And we evaluate this logistic function on the dot product beta dot xi. So xi is our data set. The betas are the ones we're trying to find. These are the coefficients we're trying to find. And the yi are the labels here. And so the loss function was given by this expression here, the average over the log of the logistic function applied to yi times this dot product. Here's the logistic function. Here's the dot product. And this is the one we're trying to find, the beta here. And so the way we did it was we wanted to minimize this loss function. We want to find the beta that minimizes this loss function. That's where we used logistic descent to gradient descent to do that. So let's see what we get in our case here. In our case, we have just 2 points. We have this point, and here the labels -1 and +1. And so the loss function here is three variables, beta 0, beta 1, and beta 2. And here's the loss function. I've written it out here in great detail. So it's minus, and then we have the label here for the first one. That's -1 times, and then we have beta 0 times, that's always there. And then we have beta 1 times the first coordinate plus beta 2 times the second coordinate. So that's what we have. That's simply what we have from this. That's the term we get from this data point. The other data point is label +1 and beta 0, and then we have 1, 1. So it's beta 1 times 1 plus beta 2 times 1. So this is the logistic regression loss function we have here in this simple case. And so what are we trying to do? We're trying to minimize this. We're trying to find beta 0, beta 1, and beta 2 that minimizes this. And that means we're trying to find out where's the gradient 0, where's the partial derivative 0. So we can rewrite this a little bit, and I'm not gonna do all the computations here, but using this well-known fact, the log of 1 over a is minus log of a, we can rewrite it like this, and then take derivatives, partial derivatives back to beta 0, beta 1, and beta 2. And I've written them down here, so there you can look at the notes I posted. So that's simply applying usual rules for differentiation. You get these things here. So we want to put those equal to 0 and see if we can find beta 0, beta 1, and beta 2. So we can try to do that. And I'm just going to give, instead of writing these all the time, I'm just going to give this term here the name A, and the other term here the name B. You can see this is sort of the only terms that appear are these terms here. And they appear then with different signs on them. So I only have these two A and B. This is A and this is B. These are the only two things I really have to compute. But if I try to write down the equations in terms of A and B, then I get these two equations here. I get three equations, but two of them are these. A plus B is equal to 0, and A minus B is equal to 0. Now the only solutions for these equations, that's both A and B equal to 0. And that would mean that, for instance, we would have A here equal to 0. But that can't happen because the exponential function is never 0. So this A here given as this fraction here is never 0. And so that means that these equations here, they don't have any solution. These equations, putting them equal to 0, they don't have any solution. So there is no minimum here. And so that's bad, because that's what we need to in order to use logistic regression. We need to find a minimum here, but there is no minimum. So this loss function does not have a minimum. And what do we do then? Well, that's where regularization comes in. So that's another very good reason for using regularization, as we saw here. If you don't use it, there is no solution. But let's try to regularize. So let's put in.
Can I make a point?
Go ahead.
Vis-a-vis the conversation we had before, that case corresponds to determinant 0. You know, so you can't solve the equation with determinant 0.
Yes
1,
and no. I don't, that
well, A plus B, A minus B. It's really.
Yeah, that doesn't have a solution, but that's right.
But morally, this corresponds to the fact that there is a determinant that can't be inverted.
Right. Yeah.
Anyway, that's
Yeah,
what I've
okay.
always
Yeah,
thought
okay.
about it.
Well, right. But this it definitely doesn't have a solution.
That we agree on.
So let's try to regularize it. And so that means we add a term like this. So we sort of for many reasons don't regularize on the constant term here. So this is sort of the one that corresponds to the one in the, so that's a constant term in the equation for the line that we're getting. So for certain reasons we don't regularize over this. So we don't only we only try to limit the size of beta 1 and beta 2. You can regularize over all three if you want, but there are reasons why we don't do that. So our loss function, our regularized loss function is now this. So we've added this this term here, and let's see what happens if we try to minimize this one instead. So we couldn't minimize this one alone. Now we added this term here, and let's see if we can minimize that. So
I have a question.
Yeah.
In the regularization term, why beta naught is not there? Why it's a function of only beta 1 and beta 2?
You can do it, but it's common not to regularize over the beta 0. The beta 0 just don't really have anything to do with the data in the sense it just gets multiplied by a 1 all the time.
Okay.
These things here, they get multiplied by the coordinates of the data points.
Okay.
So it's you can do it. I mean, it doesn't make things go wrong if you do it.
Okay.
But let's just try to see what we get now for the partial derivatives here. So the last term, well, if you take partials here, it's the partials of this plus the partials of this. So it's very easy to take the partials of the sum of two functions. The first one here, that's doesn't involve beta 0 in the second term. It's only involved in the first term. So that gives the same derivative with respect to beta 0. So we take the partial of the regularized function here with respect to beta 0. It doesn't change anything because this is just the partial derivatives of this function here with respect to beta 0 is just 0. So we get the same, a plus b. Mm-hmm. Then we take the partial with respect to beta 1. So that gives us the partial of this one with respect to beta 1 plus the partial of this with respect to beta 1. Well, the partial of this with respect to beta 1, a minus b with respect to this one with respect to beta 1 is just 2 lambda beta 1. Down here, with respect to beta 2, it's a plus b, and then the partial with respect to beta 2 here, which is 2 lambda beta 2. So we get these three equations here. So these are the partial derivatives of the regularized loss function.
Hey, Niels, just want to, it's a minor thing. There is a typo there on the last line. It should be 2 lambda beta 2. Partial with respect to beta 2 is the original term a plus b plus
here it should be, yeah, you're right.
Yeah.
Here, yeah.
Yes.
Right. So let's see, can we solve these equations here? And
Professor, can you do a slide back? I just want
what's that?
to understand how the partial derivative with respect to b1 is a minus b. I just want to see the previous slide, I guess. I didn't follow that.
Yeah, because that's just to not have to write this all the time here.
Right.
Right. So this is, I introduced this notation A and B for these. So if you go back here and see what you have here, it's A plus B here and A minus B here and A plus B here. So you can see what these expressions here for the partials in terms of A and B just gets yeah, you can see these two are the same, right?
Right.
So A plus B, and this one is the same with a minus here. So Yeah. So yeah, so the three equations that we had before we regularized, a plus b, a minus b, and a plus b all equal to 0. Now we have this extra term here, and they're still equal to 0. So that gives us a plus b is equal to 0. So this must also be, so this is 0. A plus b is 0. So that gives us that beta 2 is 0. So beta 2 is 0, and that means it drops out. And what we end up with is this equation here. And you can see that if we, so these are almost the same here. There's a minus here. So if we put beta 0 equal to 0, then this term here and this term here are the same. And this one has a minus in front of it. So in that case, it's 0. So if we have beta 1 equal to 0, beta 0 equal to 0, and beta 2 equal to 0, then the partial derivatives are in fact equal to 0. And so that means that a minimum is of this form, 0, comma beta 1, comma 0. And any point of this form will have all three partial derivatives equal to 0. So this is the minimum. This is the minimum of the regularized loss function. And so what is the line that the separating line that this one this point here, this beta here defines? Well, that's beta 0 plus beta 1x plus beta 2y equal to 0. And so this is 0 and this is 0. So it's beta 1x equal to 0, which we can also say that's just x equal to 0. So the separating line is the line x equal to 0. That's the same as the y-axis. Hooray.
That's what I guessed, by the way.
Good. Yeah, you're a good student, Adam. So you got it good. So even so, going through all this stuff here, we can see that the regularization gives us the right answer. But if we didn't regularize, we could not solve this problem, though we could.
Adam and I guessed it before doing all the math.
What's that?
Adam and I guessed it before doing all the math that it will be x equal to 0.
Right. You get a star.
One of the questions that I had was that the choice of the word regularization. If you could just two sentences on that, as well as was there anything specific to the example that we chose that caused the first order loss function to not give us, and the second order loss function to actually give us a minima? I mean, I shouldn't call it second order loss function, but the second form of the loss function.
Yeah, there is. It is in fact true that if you have at least a two-dimensional, if you have a two-dimensional data set, so your data vectors are two-dimensional, and they can be separated by a line. So if you have a whole bunch of things like this, so let's say you have data points here, and here, and some. If they can be separated by a line, so that normally you can't separate it completely. So you try to find the best line, and then that's the one that misclassifies the least number of points. But if there are no points that are misclassified, so you can find a line that completely separates the two, then then you will not have a solution. There won't be a minimum of the unregularized loss function. So this is
very counterintuitive. I mean, from a non-mathematical point of view, this is extremely counterintuitive that here you have a data set that exhibits perfect information, and we are unable to capture information. For data sets that do not exhibit perfect behavior, we're able to capture that.
Exactly.
So maybe an intuition is to say, if they're perfectly separated, it's kind of like the boundary is one-dimensional. It's like a linear one-dimensional thing. And then you're getting into the determinant equal to 0. And so something along those lines. The same way, you know, if you have two lines, they normally will meet in a point, but if they're parallel, they don't. So
fair point.
Okay, so two parallel lines, you know, funny things happen.
It's not so hard to prove it actually that it does. You can if you try to sit down and try to prove it, you probably can. It's not so difficult because you just say, okay, I have two data sets and I have a line that completely separates them, and then show that there is no the partial derivatives do not have a common zero.
But Niels, kind of speaking like a physicist, the situation is that if you wiggle the line a little bit,
yeah,
there is no significant change to the loss function because the points are perfectly classified. There is no penalty, right? So there is a degeneracy. There are many equivalent lines that differ by small deviations that do not change the loss function significantly. And the moment you add that quadratic term, that degeneracy is broken.
Yes, that's
no, but even if you wiggle the line, Vijay, it won't be you're saying that the line will be quadratic, which will be separating.
No. Right now, if you just wiggle the line a little bit about the
x-axis, I mean that's you sort of have well, I mean you can have a situation where you have a point here and a point here. And so you can wiggle it,
points all on either side of the x-axis, then this degeneracy will get kind of broken, right? But we are talking about a continuum limit here, so you're never going to get that many data points to fix this line. So
no, you're not going to get infinitely many, but it's still right. But
so in other words, the minimization we're doing is trying to rotate this line and see whether the loss function increases as we rotate this line. Right? If there is no way to rotate the line without increasing the loss function, we found the minimum.
Yes, that's true. But that's certainly true. But the thing is that in general, when you don't have total separation, right? Then you will have then you can sort of wiggle your
but now additional points will get classified, misclassified, or classified. So your loss function will change a little bit.
Yeah. Then your loss function will change, right? That's right. Here it's here it's it will not change. Because it's separating. So every point is, but it's as I said, it's not so difficult to prove it because every point is perfectly classified, right? And
but I think Niels, what I was trying to highlight is maybe it's not it's not because every point is perfectly classified or not, but there are many equivalent lines that have the same penalty. Right, and therefore the minimization is not able to pick one of them. Right, so if you're trying to find, there's no.
But Vijay, sorry, if I can say that your argument would be true in any case, right? In any defined, non-defined, well-classified, non-well-classified situations, your argument may well be true. Then why stop only at the square term? Why not say that, well, you can now nail it down further by adding a fourth power, fifth power, sixth power?
No. The idea is, first of all, in general case where the points are intermixed, if you wiggle the line, you will typically change the loss function because one point will be adversely affected or another, right? So the general case is, in some sense, slightly better behaved. Why the quadratic function and not some other function? Quadratic is nice in many ways. The U-shaped function.
You could use another function too. In this case, you could obviously use any power function. That would give you the same answer.
Just a small question here. What if you used this in places where you did not need to use it? How would that change? Does it ever get it to misbehave, or it is only a decaying factor, so you'd never get it to misbehave?
Sorry, I didn't understand your question. Say it again.
No, let's say we did not achieve a situation where we ever had to we could not minimize the loss function in the first power. And then we went ahead and said, okay, because I have to write a computer program, so might as well add the loss function at second power, third power, fourth power, fifth power.
That's right.
Would I be making some kind of broader generalization than I should have, or you should only use it when you need it?
No, no, you wouldn't. I mean, it's that's why in scikit-learn, they automatically regularize. I mean, you can change the degree of regularization by changing this parameter lambda, right? So we put in this parameter lambda, which sort of determines the amount of regularization that we put in. So the larger lambda is, the more regularization you put in. So lambda as soon as lambda is non-zero, you have a regularized problem. And in sklearn, you always have a non-zero lambda here.
You can also point out, you can change instead of beta 1 squared plus beta 2 squared, you can use different powers.
Yeah. That's
how. Right. But maybe the point of this is the function doesn't have a minimum. What that means is, no matter how large you go, you can get smaller and smaller values, right? So what this regularization term says, all right, I understand the minimum is basically out at infinity.
That's it.
Okay, because there is no minimum. But if you sort of go out to infinity, it can't be blowing up. It can't be getting too large and larger, because if it keeps getting larger and larger as your betas get larger, that would mean inside that smaller space there was a minimum. If it's always bigger when you go further away, then this the smallest value somewhere in the middle. So it has to keep getting smaller and smaller and smaller. So you can make it really close to zero by taking beta 1 and beta 2 and beta 0 really large. So when you add this regularization term, it says, okay, I know you can't do it, because as I make my bigger and bigger balls, my values get smaller and smaller. But what's the smallest I can get inside this ball? Now, it's arguably on the boundary, but there is a minimum value.
Right. Yeah, I mean, that's
functions at minimum
exactly right.
On sets that are bounded.
That's exactly right.
Compact is the correct technical word.
Right.
But
yeah, the truth of the matter is that the unregularized loss function, it does have a minimum, but it's just at infinity. And but we can't really deal with infinite number here. So when you regularize, you only look at things inside a bounded set, and that's why then that minimum will be at the boundary. That's what happens. But any convex function does have a minimum, but that minimum may be at infinity. If you try to draw this, you'll see that if you draw a one-dimensional slice of it, you see that it decreases, the derivative decreases very, very slowly towards zero at infinity, but it never gets there. So once you sort of enclose it in a ball, then it'll at the boundary it'll be the minimum. So that's so that shows that that's certainly one reason why regularization is very important, and it is you will always in practice always include a regularization term with a non-zero regularization parameter. You can make that regularization parameter very, very small if you don't want to regularize too much. So that is one reason why we regularize. So another thing that we saw last time was the convergence rate of gradient descent can be painstakingly small. It can be so small that in practice you can't find the limit using that. and we saw that even in sklearn, you didn't find the right minimum using that. And now there are ways in you can change that in sklearn to actually find the correct minimum. But I will just now I'm not going to go through all the math here because it's a little complicated. But you'll have to look at the notes here. But the idea of Newton's method is to, instead of just using first order data, namely just using the first order derivatives of the function, we get the gradient descent. But if you use second order, you get another method called Newton's method, which converges very, very fast. And let me just not go through all the details, but the idea behind the gradient descent here is that you can approximate a differentiable function with a linear function. And so the linear approximation to a function is f plus delta x is almost or is close to the value at x plus the derivative of the function at x times the delta x. So that's the linear approximation, and then by using some theorem from linear algebra, you can show that in fact the fastest descent you get here. So when you want this difference here to be as small as possible, and that happens precisely when this delta x here is a multiple of the gradient. So it's in the same direction as the gradient, and you want this to be negative, so you want this to be 0. But you can also use a quadratic approximation to f. So this is a more complicated expression here where you have that f of x plus delta x can be written approximately as f of x plus the gradient of f times delta x. So this part here is the same as before, but then there's an extra term here that involves the double derivatives of f, and that will have delta x as a quadratic term here. So this matrix here, not the square here, as I call it here, that is the matrix of double derivatives. So you can, when you have a function of several variables, you have its gradient, that's the partial derivative x of partial derivatives, but you also have if it's also twice differentiable, you also have the double derivatives. You can take the derivatives with respect to one variable, and then you can take the derivative of that with respect to another variable. So you have all these cross derivatives here. So that's what I've written up here. This matrix here is the what's called the Hessian. So that is a matrix of all the mixed and also the double derivatives with respect to the same variables here. That's down the diagonal. So that's a matrix of dimension d, where d is the dimension of the variable x. So if we use that, then we get, again, I'm not going to go through the math here, but if we use that, we get a particular delta x that we should use in our gradient descent sequence. That says take this Hessian, take the inverse matrix of the Hessian and multiply that onto the gradient and take the negative of that. That is your delta x, and that's what we use in the Newton sequence. So again, we start with some x, then we compute this delta x here, and then the next one we use is x plus delta x, and then we do the same with this new, so this is now x1, and then we do the same next time we get x1, and x1 plus delta x1, that's x2, and we continue this way. And that is going to converge to a minimum, and it converges very, very fast. So I've done it for logistic regression here, computed all the double derivatives and stuff. I'm not going to go through this because I would get confused myself if I did that. But you can easily follow by if you go read the slides, you can easily follow along and verify the computation. So
then on the previous slide, sorry, one question. So on the previous slide, with the expansion of fx plus delta x you were doing, in one dimension, is this what a Taylor series is?
Yes, that's a quadratic Taylor.
Okay.
Yeah, a quadratic Taylor polynomial. Exactly. I mean, it's a polynomial. It's a quadratic polynomial in delta x. What happened? So I computed this, as I said, I computed the Hessian for the logistic regression loss function, and you get a sort of a fairly nice formula. It's not so difficult to program. And in fact, also the code file I gave you also has the code for how to compute the Hessian. So I have applied this to the data set we had last time for the temperature and the loss function of the Challenger data with the temperature. And so as you remember that we started there at the starting point of 0, 0. So beta, we started with 0, 0, and then we used gradient descent, and we never got to the true minimum of the function. So let's try to, instead of using gradient descent, let's now try to use the Newton method here. So this is what we're doing here. So here we start with a B, and then we take the inverse of the Hessian. So I computed the Hessian up here in code here, so you can also try to run this code. And then I multiply that by the gradient, minus the gradient, and then I have to take a minus, it gives me plus here. And then I can run this, so I run it only for 10 iterations here. And you can see here, the result I get here is that this converges already within 6 or 7 steps. So after we get down to here, there's no change in the level. So it's converged already in 5 or 6 steps. So this is and you can see here we get the correct minimum now. There was about this 15 comma minus 0.23 or something. So that was the same we got from the other methods. So this Newton method here is very, very fast. It converges very, very fast if it converges. I mean, if there's no minimum, obviously it does not converge. But it's a little harder to compute, right? Because you need this second order information, these double derivatives. So it takes a little longer to compute. But you can also use this method in sklearn. So what you have to do is here's the logistic regression class, and here we instantiate a logistic regression classifier. Instead of, if you don't write anything here, then it'll use the solver lib linear, which is the gradient descent. But if you use other solvers here, this is LBFGS, so this is a low memory. I can't remember this. Braden, Fano, Goldfarb, and Shannon or something. There are 4 guys who invented this optimizing method here. If you use that instead, then in fact you do get the right result from that. So if you're having a problem with getting your logistic regression from sklearn to converge, you can try to use another solver. There's also a Newton. I think in the code I posted, it's a Newton CFG or something. That's another solver that uses the method. So you can do it with sklearn also. So here's sort of an illustration.
sklearn will by default use the liblinear, the linear term which converges very slowly.
Will use gradient descent. So it will not converge.
So sklearn by default uses liblinear solver.
Right. Exactly.
Right. Okay.
That's the fastest. That's that's the fastest.
Okay.
So this one it takes a little bit more computation because you need to complete the second order.
Okay.
So here's sort of what it looks like when we do this in a one-dimensional. So we start with this point here, and here the green one is the quadratic approximation, and the orange one here is the linear approximation. And so what the Newton's method does, it said, okay, I'm going to approximate my curve with a quadratic one. And then I'm going to say, well, the minimum of this quadratic one is probably going to be close to the minimum of the curve I'm approximating. So here's the minimum of the green curve. That corresponds to this point here on the blue curve, which is the actual one. So that means that the next point we're getting is this point here. And then we do the same. We find the quadratic approximation that approximates the curve at this point here. So that's, again, this green curve here. And then, again, we say, okay, this quadratic one is close to the curve. That means that the minimum of this quadratic one is probably close to the minimum here. So that means the next point we're getting is here. And you can see here from this, keep doing this a couple of times. You can see the green curve here, the quadratic curve is now very close to the blue curve here, and the red point here is very close to the minimum. Here, in fact, we are at the minimum. The green points here, those are the ones we get by using gradient descent. You can see it goes much faster here, much slower here, rather. It converges much slower. It's much further from the minimum than the red point. Also, you can play around with the code that I posted, and you can sort of see how this thing works. I put a little piece of code in there, so you can run this algorithm a number of times and see how the Newton method converges much faster than the gradient descent. So we can also use Newton on the regularized function, of course, and that is again pretty simple because again, well, all we have to do is to again taking the double derivatives. Again, it's just the sum of the double derivatives of the loss function, the unregularized loss function, and the double derivatives of the regularization term. And the regularization term is, if you use quadratic regularization, is very simple, right? Because what's the partial derivative of this beta 1 squared with respect to beta 1? Well, that's just 1. You take double derivative. First derivative is 2. So it's 2 beta 1, and then the next time you take the derivative of that with respect to beta 1, you just get 2. So it should be 2. That's why people prefer to put a 1/2 here. So the Hessian of the regularization term is just this matrix here. We left out the beta 0, so we get a 0. So it's just a matrix that has ones down the diagonal except for the 0 up here, and then you multiply it by. So this is a very simple term. You're just adding that to the you're adding this to the Hessian of the
loss function,
unregularized loss function. So it's very simple to regularize the Hessian. And also there's some code here that shows how you do this. So this is computing it for the for the regularized thing. So one thing you should notice here is that once we do this, once you regularize, and now I'm regularized with a somewhat larger regularization constant 6 here, then you can see what happens is that the actual solutions you get, the betas here, are much smaller than this. So before the minimum was at 15 or something, and now it's much smaller. Now it's the constant term there is 6.98, and the other term is minus 0.11. So you're getting different minima. So that's what happens when you regularize. Your minima is going to be different because you're restricting your minimum search to a smaller subset. So you're going to get smaller. You're going to get a ball, yeah. And so they'll be smaller. And so that's not something to be afraid of because that's to be expected. That if you regularize, you're going to get a different minimum than you get on the unregularized. So logistic regression in sklearn always uses regularization, but they do it by putting lambda equal to something of the form 1 over c, and so that can never be 0. And so, but that means that the bigger c is here, the smaller lambda is. So you have to be careful when you're doing sklearn. When you regularize, a very, very large constants there corresponds to a very, very small regularization parameter. So that's something that Adam in particular is really pissed off about. But that's to make sure that you always regularize. So you should always get a solution in sklearn. Yes, I will not. So here's just the regularized logistic regression using the LBFGS thing. So I will quit here because Adam has a lot of stuff to talk about. So I will. So there's some. So you should submit your homework, right? And we have made another homework here, which is somewhat simpler. So we're only going to give you 1 week to do that, and so they're at the end of these. Okay, so next is Adam, and let's see.
So I have a couple of questions. So logistic regression, which we did so far, it used 2 labels, but it may very well possible that we are dealing with a data where you can have 4 or 5 labels, like 1, 2, 3, 4.
Yeah, that's right. Yeah, that's right.
We still can't do linear regression. We have to use logistic regression. So it's still possible, right?
It's still possible to separate those. Yeah, definitely, it is. There's another technique which is a generalization of logistic regression, which is called softmax regression, which allows you to do when you have multi-label, multi-category categorization problems. So you can do that. You can also sort of do it one at a time, right? You separate one set of so let's say you have 5 categories. Then you separate with logistic regression 1 category from the other 4.
Okay.
And then you do the same on the remaining thing, and you separate those from the rest of the 3 of them. And so you can do it one against the other, and that way you can get them separated. You can use logistic regression, but there is a technique called softmax regression that can do this. One fell swoop there. So that softmax regression we will be looking at, because that is a very important thing in when you use neural networks to classification problems in neural networks. Yes. So let's see. We should stop sharing here, right?
Yes.
Okay.
So this is the slide I'm surest about. Any questions on this? Okay. All right. So I'm just going to give a slightly different take on regularized regression. And I'm mainly going to discuss it in the context of linear regression as opposed to logistic regression. As Neil showed, everything he said about, everything, I'm going to say about regular regression will work for logistic regression as well. So regressions can have two purposes. They can be descriptive or predictive. You can either just sort of say, I have this data, what can I say about it? Or you might want to say this data is representative of more data. Can I predict what will happen in new cases? So as long as you're just interested in description, more variables you have, it's always the better. However, if you're interested in prediction, this is not always the case. So there's a few problems that can arise, and I've listed 3 of them. And too many variables can lead to modeling the noise. So in other words, you understand that unless your data set is perfect, if there's no noise, in which case there's no need to do machine learning, your data information is not perfect. And if you have too many variables, the noise components become more and more important. And another problem is, and this is something we were talking about earlier, is that highly correlated variables can lead to unstable models. So if you just have variables that are highly correlated, but not perfectly correlated, the matrix that you get in linear regression, this X transpose times X inverse, will have determinant, well, the determinant will be very small. And so small changes in your data are going to lead to very large changes in the matrix. And what this means is that small changes in your data points will lead to very large changes in the coefficients you model. And this is what we're calling unstable models. Will that thing work on here or not? I don't think it will. Will it? The red pointer.
We can make it work.
Okay. So let's do that for now. So those are the things. So point 2 is the most important because if you have slight changes in the data leading to very large changes in your model, that's an evidence that your model isn't going to be good. So we want to avoid having to do that, but your data is your data, so what can you do? And the answer is your model is not your model. Okay, so maybe this isn't going to work so well. Go back to the other one. Right. Now I remember this happened last time too. Okay, so as we were saying before, regularization is a way to deal with this. So in general, what regularization does is it penalizes coefficients for being too large. Now, in the context of what I'm just saying, this is important because if you don't allow the coefficients to be too large, then then small changes in the data cannot lead to large changes in the coefficient. If you somehow set it up, just to simplify it overly, that no coefficient can be bigger than 10, then no coefficient is going to be bigger than 10 no matter what happens to the slight change. Okay? Okay. So, so just to keep us all busy, here's a quick quiz. If I have a regression and I add more variables than R squared, which is a measure of how well the data will fit, will it always go up, always go down, or it depends on what kind of variables I add? What do you think? Okay, so we have percentages. 50-50 for it always goes up, and it depends. And now we're going to always goes up. The ensemble wins. Always goes up is the correct thing. If you add more variables, even variables that have nothing to do, like let's say you're trying to predict the price of tea in China, and you add variables about orange juice prices, which has nothing to do with the price of tea in China. the R squared will always go up. Let's see what's going on here. Okay, so this will lead to a model. So if R squared always goes up, you have to be, what that means is you have to face the possibility when you're adding more variables that you're modeling the noise and you're going to get poor predictability. So to illustrate this, I want to do a simple example in R. So what does this code do? I just set a seed for reproducibility. So every time I do this, I will get the same numbers. And I sample the numbers from 100 20 times and divide by 20 just so the numbers aren't so big. I'm getting numbers between 0.05 and 20. And then I do the same thing. And I create a noise variable, 20 random samples of a normal distribution with mean 0 and standard deviation 5. And then I just have more noise, which, I mean, it looks kind of complicated, but I've taken 100 samples of just random noise with mean 0 and standard deviation 1, sort of normal random noise, and written it as, well, I have 100, so that's 5 times 20, so I've written it as 5 20-column matrices. So it's just 5 more noise variables. And then I create my dependent variable. I just look at a linear combination of x1 and x2, and I add the first noise variable. And then I create 2 data sets. The first one is I'm just looking at my variable, which is completely determined by x1 and x2. And the next one, I've added to x1 and x2 these 5 noise variables. So what's going to happen? So as I say here, the second one is just the first one with a bunch of noise. You saw the variables that I created have absolutely nothing to do with the data set. The data set 1 should do a better job of predicting. So let's compute R squared for both of them. So R, everything's an object, and the R squared is part of the summary. And so if I can push this down, you can see it. You see for the first one, we get an R squared of 0.69. Right. And what about for the second model? Really, the second model should be no better in terms of predictive ability or descriptive ability. But yet we'll see that when we go through this, we see R squared has gone up about 10 points from 0.69 to 0.79. So there you go. I've added noise, and what I've done is clearly if I was going to predict future cases, model 2 would be worse, but because it has more noise, it's got worse coefficients, but nonetheless, R squared goes up.
So that's simply because of the formula for R squared, right? That does it. The more variables you have, the higher.
Well, yes. So what R squared is telling you is sort of telling you what percentage of the variance, your model is describing. Right. So even if your new variables are noise, they can still be used by taking the right coefficient to explain some of the variance. So small bits of variance, and noise are being confused. And as I say, to give linear model credit, it does correctly predict which 2 variables you would care about. It does say that x1 and x2 are the only ones that are significant. Okay.
So here one question, a couple of comments. So normally adjusted R square is something which is considered to be a better measure if you're adding more variables. And here I see that adjusted R square also increased. So even adjusted R square is not a very robust measure of checking the predictability or the importance of predictors.
Right. So adjusted R squared was specifically introduced to deal with the fact that when you add more variables, you're always going to improve. So, but it's a kludge. There's no theoretical justification for our adjusted R squared. Right. It's going to do better because it's taking some account. But there are way more sophisticated things. I don't know if we'll talk about them, like the Akaki information criteria.
Right.
Where you can see very clearly that when you want to sort of say how good is the model, you look at you look at how well it works. but you have to multiply it by a factor that's related to the number of variables. And the more variables you have, the sort of a priori worse the model is going to be. So if you have two models that look exactly the same in terms of what they predict on the data set you have, but one has more variables, the Akaki information criteria will say absolutely, the one with less variables is a better measure. But that has a good statistical justification, unlike this. And while I didn't show, I just talked about R squared to keep, very, sort of simple. The adjusted R squared also does go up. Okay.
One more question I have is, let's say even if we added some noise variables, right, which has nothing to do. But given if we have enough data, the coefficient of noise variable will go towards 0, wouldn't it? Because it has no meaning, so regression coefficient will get closer to 0.
That's true. It's always a function of sort of how many data points you have versus how many variables you have. But you can make mistakes. You could be unlucky.
I mean, you have tests. I mean, significance tests. You have like t-tests and f-tests, but there are. I mean, the fact that it's t-distributed again is it's an asymptotic thing that sort of relies on or works if you have lots and lots of data. Hopefully. I mean, at the best possible case, infinitely many data. So you're using in order to test whether some of these variables are 0 or significant. You rely on asymptotic distribution, the sample distribution,
and so I'll point out, if I'm a classical statistician, I'm probably then redoing the model with only the variables x1 and x2 because the t-test is saying or suggesting, it never says, it suggests that the only two variables that count are the variables x1 and x2, which makes sense because those are the two that really determine why. But it's a complicated thing. I mean, I don't think it's true that just by adding enough data you can distinguish which truly important variables from others. And as a practical matter, once you have hundreds of variables, these kind of tricks aren't going to work. You need to really have some better way of deciding what's important or not. But in any event, this data set was tailor-made to illustrate the point that R squared goes up, but you're not improving anything necessarily. And that we need some way to deal with this. And notice that some of these coefficients of the noise variables are reasonably large. Any other questions?
Yeah, I think Tejas has a question, right? Tejas, I see a hand raised there.
I think that was a mistake. Sorry.
Oh, that's a mistake. Okay.
No?
No, that was a mistake.
Okay, so we're talking about why you would regularize and when you would. So one case, and I just want to talk about this very, very briefly, I just mentioned it because it can come up, is if you have more, the opposite of what you were talking about, Manish, if you have more variables than you have data points, then it's essentially impossible to write a good linear model. And this does come up in various fields. It typically does not happen in finance where there's huge, huge amounts of data, but there are fields, including text analytics as an important current one, where this can happen. And one of the results of this is, in this case, the matrix is always, I wrote is non-singular, but I really meant to write singular, so that's a typo. And there were traditional ways to deal with this, but the problem with them is with modern data sets, once you have more than 10 or 20 variables, depending on exactly what you're doing and how powerful your machine is, these methods become too time-consuming to be practical. So, when there's more variables than there are data points, regularization is essential. But there are lots of cases when there are way more data points than there are variables, and regularization is still useful. Okay, so here's another quick quiz. If I have a data set with 1,000,000 rows and 500 columns, what is N and P? And question 2, is that a large data set? So the first one, what is N and what is P? So does everyone answer, or is that just one answer?
I think it's just one answer.
And
We got just one.
All right. Well, I mean, I just wanted to keep you engaged.
No, we got yeah.
Okay.
We got one more answer.
Okay. So one is right, one is wrong. N is 1,000,000. Could you pull that down, because I can't really see? But I think I remember it was 1,000,000 rows, so N is 1,000,000, and 500 columns, so P is 500. That's just, there's no reason why it has to be, but we've always talked about N by P matrices. So this would be 1,000,000 rows, 1,000,000 data points, 500 columns, 500 predictors. Is that a large data set? Now, everyone can have an opinion, but my point is that's just an opinion. Is that a large data set? Depends how large your memory is in your computer. I mean, 20 years ago, that was a humongous data set. Nowadays, on most laptops, it's tiny. So one of the points is that you can have data sets with lots and lots of predictors that aren't particularly large nowadays. And as people get more and more space, we get more and more predictors, and this comes up. So regularization is a way of dealing with the coefficient problem and the problem of them being too large. Now, remember when Niels was doing the logistic regression that didn't converge, the problem was as the function basically took larger and larger values, it got smaller and smaller. So if you took any area centered around the origin, you would have a minimum on that, but it would be right on the boundary, because as soon as you got to a bigger ball and the function could get further away from 0, it got to a smaller value. Should we whiteboard this?
yeah.
Okay, well, I'm going to go to the whiteboard, and illustrate this. Just a point. So in this case, that's the origin. If you looked at a circle of that size, this logistic regression, that would, I'm just being arbitrary, but it would have a smallest value here. But if you drew a bigger circle, maybe, as the thing is sort of wandering around, now the smallest value is here, but it's always going to be on the boundary. And I can't draw a three-dimensional, but these values are going to be, this one is going to be bigger than, this value is going to be smaller than this value, and this value is going to be smaller than that value. And one of the points is I've drawn circles, but I could just as easily draw squares. But it's always going to be the case that whatever shape you draw, as long as you bound it in the region, you can get smallest values right on the boundary, because whenever you're going further away, the value is getting small, the smallest value is getting smaller and smaller. And so what this means is that as the coefficients are getting larger, the value is getting smaller. So the only way to get this to have a minimum value is to say, all right, I'm going to demand that my coefficients be in this box, then it's here. I'm going to demand my coefficients be in this circle, then it's here. I'm going to demand my coefficients be somewhere inside this circle, then the minimum value is there. So the idea is that by using this method of regularization, you are guaranteeing that there will be a minimum. Because a function has to take a smallest value. Nice function, continuous functions like these, has to take a smallest value in a bounded box. Now we have to share the screen again.
So a question, like when we are having this, with regularization, we are having this bounded sphere or n-dimensional object. Is it absolute value, or it also depends on the standard deviation of the predictor? Because a predictor having a very high standard deviation can have a small value of coefficient, and having a same predictor A second predictor having very small standard deviation can have a bigger coefficient, right? But if it is not taking into account the standard deviation of a predictor, then absolute value may not be the right way to regularize.
Well, as I get through examples of boxes and circles,
right?
And the point is it doesn't really matter, you know. So whether it's absolute value or squares, you're going to get different answers for sure. And there is a nice picture which I've taken from the web that shows it, you know, a few slides further down. But you know, there's also certain cases where, you know, you sometimes you don't need to regularize. But for prediction, you almost always will, because somewhere between philosophically and morally, if you don't impose these kind of bounds, you will always model the noise. The regularized solution will rarely be essentially never be well, in a correct sense, the regularized solution will almost never be the regularized solution will always outperform an ordinary regression for prediction. So, you know, regardless of these things.
Right. Okay. So let me ask my question in another way. Let me explain it. Let's say if we have y equal to x, right? So the values are perfectly correlated, right? So the beta will come out to be 1 if we do regression, right? Now let's say if I multiply my x values by 10, okay? So x is the same thing, but it becomes 10 times bigger, right? So beta will come out to be 0.1, right? Let's say if I shrink the x values by 1/10, then beta will come out to be 10, right? Because x is 1/10, now beta will become 10 times. So if we are looking at regularization by just having some absolute, the beta cannot be bigger than some absolute value, like not bigger than 0.5, then that may not work unless it is taking into account the standard deviation of the predictor as well. I'm pretty sure it must.
That's what you mean now. Yeah. No, the answer to your question is absolutely, and we'll see this in a second. And so you've basically stolen the thunder from my next quiz, which was asking this, and I just don't call it. I think of it as scaling, not standard deviation. But yes, I mean, because of scaling issues, it's important so I'm skipping ahead. If you're going to do regularization, it's important that you scale. Okay. So when you do regularized models, the first thing you do is you scale your data matrix, by which I mean all the data, you know, points, you find them, you subtract off the mean, and you divide by the standard deviation. So you get points with mean 0 and standard deviation 1. I mean, for exactly the reason that Manish is saying, if you don't do this, the whole process becomes meaningless, because you can rescale the variables and make betas as small as you want or as large as you want without changing any of the information. Oh, wait. It's right, the last point. One important point. It's important that data be properly scaled to use these techniques.
Okay.
So we're actually right on the slide. So the next thing I should have been saying is what he said, that it is important to regularize for exactly these reasons. I mean, that allows you to sort of have a standard universe of betas. Okay? Any other questions on this point?
So yes, Professor, so the way we define those boundaries, right, the one that you explained, is by what Professor Niels explained, by defining the lambda, right, like 1 by c. Is that how you define?
No, I will get into that in a second, but lambda, okay, so lambda is not shown in that box. Lambda is the amount by which you regularize. It can be small or large. It's sort of saying, how much do you really care what the penalties is? And we haven't talked about this yet, and you know, but the choice of lambda is important in the end. So let me say, you know, so you have this free parameter lambda, which means that there's not a regularized solution. There's infinitely many. I could take lambda equal 0.01, and there's no particular good reason here to take lambda equal 1. It may or may not be, but maybe lambda equal 2.718 is right, or lambda equal -17. How do you know what the right lambda is? And the answer is, you're really interested in prediction, so you want to see which lambda will give you the best predictive values. And typically, you know, and beyond typically, the absolute standard way is to use cross-validation to find the lambda that gives you the best prediction. So you may take your data set and divide it into 10 pieces, use 9 of the pieces to train a model with a given lambda and find, you know, how well different lambda predicts on the 10th piece. You do this, you have 10 possible divisions, so that gives you 10 estimates, you take an average. And so for that lambda, that gives you an estimate of how well the model predicts with that lambda. Now, you know, what you do is you just take a large grid of lambda. You know, really nothing to take lambda, say, from point, you know, from 10 to the minus 10 to 10 to the 10, differing by 10, and start off that as your grid. And then, but this is a numerical method that are used to find the appropriate lambda. So how much regularization you use depends on the actual data, and you use cross-validation to find the lambda that will give you the best predictive values.
Yeah, this is what the lambda is, what a hyperparameter, which is sort of is something that's external to the model, and it is something that will be chosen as Adam said, by cross-validation or grid search to find the best possible lambda that performs that using cross-validation has the best performance. But it's you can it's the larger lambda you take, right, the more you shrink your domain. So you, as we also saw, the smaller, a larger lambda would give you smaller values. So a large lambda will correspond to a smaller area in which you search for your minimum.
So I think in the next slide or two, I'm going to discuss this more explicitly. So let me just see. Oops. Okay, yeah. So there it is. So ridge regression works by penalizing the L2 sum of the coefficients, and L2 means just the square. So recall we have the residual sum of squares, which is just the difference between your actual values and your predicted values. I mean, this is your loss function. You want this to be as small as possible. If this is 0 on the nose, it means you've predicted the exact values of y. And I've just rewritten it out there. So OOS, ordinary least square, amounts to finding the beta j's, the coefficients here, which minimizes RSS. Ridge regression says you want to find the beta j, which minimizes the sum of these, you know, the loss function plus the sum of beta j's. So I didn't write the lambda there. So, but the problem with ridge regression is to find the beta naught through beta p, which minimizes your actual loss plus the lambda. And here, again, as Neil said, you only use the coefficients of the matrix, so you don't regularize the constant term. And I'll discuss why in a second.
No, look, just that if you look at that formula there, you can see it's exactly the same formula. It's just the different loss function. Here you have the squared loss function. Before we had the logistic, what's it called? Let's go the cross
entropy. Yeah.
Cross entropy loss function. But we just had a different loss function, but the same regularization parameter, the same regularization term. So it's just the same thing. A loss function. Every time you have a loss function, you can regularize it by adding something like this.
Yeah, this is the penalty term, and this lambda is at the moment completely unspecified. Okay. So as we said, you know, with these circles and squares I drew on the board, this is equivalent to finding the minimum of something subject to the constraint that all the beta I squares are less than some fixed value. Or actually, I'm sorry, that really is a typo. It really should be the sum of the beta i's. I mean, you could do that too, but that's something different. And how you go from lambda to this m is complicated, so we don't write it out. So in essence, ridge regression amounts to finding the ordinary least square solution subject to the beta i's lying in some fixed ball. Okay? So why don't we include the constant term beta naught? For regular regression, it's actually pretty clear. Otherwise, when you let lambda get really, really large, when you sort of put enough penalty, you get all the beta i's were equal to 0. Because then the only way, I mean, think about it. If anytime the coefficient is non-zero, you put a penalty of 1,000,000 on it, the best solution is probably to be to just say, well, I won't have any coefficients. So you would just get the dumb solution of when lambda goes to infinity, that my best solution is to just guess 0. But we know that if you don't have, that there's a better guess. If you just want a constant guess for your solution, the best constant guess is not always 0, but the best constant guess is the average value of the y's, right? If I'm just told I have to estimate y1 through yn by one number, the best estimate is the mean, not 0. So if you penalize the beta naught, you don't get this estimate of, I'm going to guess the mean of the yi's, you get, I'm going to guess 0, which makes no sense. So that's one reason. And once again, as you know, to echo what Manish said, to run reg or any regularization, one first normalizes the data set by scaling the variables to have 0 mean and unit variance. And frequently, although again, this is, you'll see this will be handled internally, you want the y's to have mean 0, which will get rid of, what does that mean? It means you're going to get rid, there'll be no beta naught to deal with. Okay, so then, you know, the issue of regularizing beta naught or not goes away completely.
You don't scale it, you subtract the mean.
You subtract the mean, yeah. So you don't scale the mean, the y's, you center the y's. Thank you. Okay, if data is normalized so the xi are scaled.
Just answer the
and the yi's are centered, do we still care about beta naught? As Neil said, I just answered my own quick quiz number 3. Is anyone going to jump in? Okay, the answer is no, because once the data has been scaled and the dependent variable has been centered, there is no more beta naught. Beta naught is 0 at this point. Okay. Okay, so now I'm going to talk a little bit about lambda, which we have given short shrift till now. And Niels has said most of this. As long as lambda is equal to 0, this pushes the coefficients towards 0. It forces them to be in some ball. It gives them some maximum size. And smaller lambda means smaller balls.
Oh.
Smaller lambda means
larger lambda
means larger balls.
No.
Oh, no, excuse me, you're right, yeah. Smaller lambda means you don't care so much about penalizing. You're gonna have to now go to
larger lambda.
That's a typo.
Yeah.
That's one that's worth correcting. Thank you. Right. So why is that? Maybe you can just X that.
What? Adam, if you replace lambda with C, it would be okay.
That's blasphemy.
That's right. I mean, this is a Pythonist who's speaking. I can hear it.
Pythonista.
Just a moment of levity at the end of the session.
There you go. It's a good thing you're not here. You would definitely get into a fist fight.
And that was me. You see, the thing is Niels is tall and he's kind of lanky. He can afford to fight. I have to be a man of peace. Yeah. But as you said, right, because if the lambda is small, that means you're not penalizing large coefficients very much, so they're allowed to live in a larger ball. And as lambda goes to infinity, as you're putting your penalties higher and higher, all the coefficients go to 0, and we just get the mean. So because of this parameter lambda, there is no unique ridge. For each lambda, you're going to get a different, you could arguably possibly get a different solution, all right? So then the question becomes, how do you choose lambda? And as I said, the typical way to do it, and maybe I'll just write this down, is, oops, I don't do this very well, use cross-validation. Looks like I'm, the nice thing about doing this is it makes me feel like I'm 12 again, because I write like I'm 12. Neil says I'm always 12. I'm not going to argue. US's, right? In my defense, I have a weird angle, but so you use cross-validation. Now, the good news is that this is nothing that you have to implement yourself in code. And I'm skipping ahead. When we get back, if you want to do this, I'll just talk. There's an absolute, in addition to scikit-learn, there's a standard package called GLMNet, GLMNet, that does this. And you know, part of the absolute standard thing is it uses cross-validation to fit the best lambda. And GLMNet can be used for both regular regression and logistic regression. So, you know, how do you find the best lambda? You say, what's the best lambda? Getting back to something I said, is the term lambda beta j squared is, it's putting what's called the L2 norm on the betas, the Euclidean norm. And it's more convenient and more common to write this as norm of beta sub 2, meaning that 2 corresponds to that true. So, and writing lambda times beta to that. And this is the L2 norm of the, in the space of all betas, the parameter space of betas, this is just the Euclidean metric.
Well, there'd also be the square of the norm.
Oh, excuse me. Yeah, no, didn't I write that? Or did we find another thing?
No.
Okay, so I didn't. So, yes. So there's another typo. And by the way, I revised this about 5 times this afternoon, finding typos. So I apologize, but I will recorrect it again before I have it, and I'll repost it. Okay. Okay, so Manish, you have to answer this question. I didn't call this a quiz, so Manish, you get to answer this. If I have 2 variables, x and 100 times x plus noise, and I ran a ridge regression, which coefficient would be penalized? More likely to be penalized.
I mean, the first one.
Absolutely, because as you pointed out, its coefficient's got to be 100 times bigger.
Right.
Okay. So why do we care about these things? We're pretty much guaranteed that the training error on our ridge regression will not be as good as the training error if we do ordinary least squared. So what's the point? And there's a few points. As Niels has said time and time again, if you use regularized regression, you're always in these cases guaranteed a solution. But let me just summarize all this by saying that the real, to me, the heart of the reason to use these things is because they work much better for prediction. I'm sure you can find a data set for which is this fault, but I've never seen a data set for which ordinary least squares regression predicts as well as a regularized regression, okay? And it's specifically because of these features of forcing the coefficients to live in a set that's more reasonable. It kind of forces some of the noise that might be brought into the coefficients to go away. So the point of this is definitely to help with prediction. And this is, Niels has discussed this on a slightly different thing, but this is another example of bias variance trade-off. Is, a very famous theorem, I think it's called the Gauss-Markov theorem, that says that if you want an unbiased, linear model ordinary least squares is the best. It's going to be the best unbiased, and unbiased means it has, on average, the right mean. Okay? So these models, these regularized models, are not unbiased. They're biased. They will not, in general, have their average expected value will be slightly off from the correct expected value. But the amount of variance that they display goes down significantly. And what that means is that when you go to predicting, this reduced variance corresponds to much better predictions. And as my last bullet point said, Niels has said this, I think this was in week 1 he made this point, and he's put it in a slightly different way, but this is exactly the point. The whole point is that ridge and lasso reduce variance and you know, the noise in your coefficients, and that makes them better for predicting. Okay, so that's really why we do it. Okay, so right, let me do this very quickly. I just thought it was unfair that Niels got to do all the math.
Come on.
And so I'll quickly run you through what's going on here. So, and it's what I'm going to do is show you a closed form of the ridge solution, the ridge equation. So we wish to minimize this thing. Okay, and this expression, if I write this in matrix terms, this is y. This is a dot product because of the squares. This is y minus x times beta transpose times y minus x beta. That's the dot product. And you see here I did get the square right. Plus lambda times the norm squared. Okay? And so if you write this out, you're going to get 4 terms. And the first one is y times y, but we're going to take derivatives with respect to beta. So we're only going to care about the terms that have beta in them. So we're going to get 3 terms with derivatives here and 1 term here. So, in fact, these are the 4 terms, and when you take derivatives, as I said, only this one and this one and this one count. Well, you can kind of see, you know, remember, you don't care about x transpose and x from the point of view of taking derivatives with respect to betas, they're constants. Okay? And the other thing to notice is that y transpose times x is the transpose of x transpose of y. And when you put that all together, you see that when you take the derivative with respect to some beta, any beta, this is what you get. Minus 2 times x transpose times the, you know, y minus x beta, and this plus 2 lambda beta, that's coming from here. The 2 comes because you have a square. Now it's just simple linear algebra. You get the beta is x transpose x plus lambda times the identity matrix times x transpose times y. Now, going back to what Manish was saying very early on about the y hat matrix, notice that this is exactly the solution you get for ordinary least squared, except for this plus lambda times I. And this shows you that essentially for all except finitely many values of lambda, this matrix will be invertible. Okay. So here it is, math. You have a closed form solution for the ridge. Okay. Okay. Yeah. So I want to talk about lasso briefly too. Sometimes ridge won't be perfect. Sometimes it will. But we should always be agnostic and try and look at as many models as we can and find the ones. So one issue with, or one thing about ridge is it'll reduce coefficients, but it'll never really make them 0. There's another method called lasso that can be used that will, it's using the boxes. It's using what's called the L1 norm. And unlike ridge, lasso will tend to eliminate coefficients. So in other words, when you run a lasso model, you expect a certain number of the betas to be 0. Now that can be useful if you have a bunch of variables and you're not sure what are important. You can use lasso to decide which variables you actually want to use. So the lasso is the same thing. Here's your loss function. And here's your regularization term, but instead of the squares, I'm using absolute value. So the only difference is the penalty term. It's the same thing, loss function plus penalty term. And this is what's called the L1 norm because absolute value is the L1 norm. Okay, and I think the first few things of these say what I just said in words. As I said, when you're using an L1 norm, that means in the space of betas, you're getting squares instead of circles. And this is, as I said, a picture that I've stolen. This comes from, among other places, Elements of Statistical Learning. And the point is the box on the right is a ridge, thing, and the box on the left is a lasso, bounded area, because in two dimensions, a square is the equivalent of a circle. Okay, and the decision boundary, what's the value of the coefficient you check? That's where the ellipse actually hits the edge of the box. So this shows why, let me just go back. This shows you why you can get coefficient 0. On the circle, there's no distinguished points. Every points are the same. But on the square, you have these 4 points, that are the size of the square. And if your decision boundary hits one of those 4 points, that means one of the coefficients is 0. Right? So you say, well, there's 4 points out of infinitely many. That isn't so big. But remember, well, a two-dimensional lasso problem is not probably going to eliminate variables. But if you go to hypercubes, now all of a sudden, like if you in 3D space, you'd have a cube, and any one of the sides of the cube, you have all the lines in addition to the 8 points on the side of the cube. If it hits any of those points, now you're saying one coefficient is 0.
Sorry, I didn't get the idea. Why sphere? Let's say if there's a sphere, there won't be coefficient won't be 0, but a cube will have it as 0.
Yeah, because the mathematical answer is that these are both quadratic, and this is a tangent line. It's just fine. When it hits one of the sides, you have the function isn't differentiable. And that forces the coefficient to be 0. It's the only way to make it work. It's specifically because you have that sharp point there at the edge of on any kind of sides of a cube or a square, you have a sharp point. And the only way you can make it take a minimum there is to have one of the coefficients actually vanish.
Okay.
Okay. So there's no intrinsic reason to prefer one for the other. Lasso, as I said, may be useful if you're trying to reduce the number of variables. Lasso can be used as a technique to find variables to remove. You just remove the ones that the lasso says is, you just remove the ones that lasso says have 0 coefficients. And of course, one doesn't have to choose, one should remove both. And as I said, in addition to scikit-learn, there is a software called GMT, and it's pronounced GMT as far as I know. And it exists for both R and Python. And it does a few things. At least in the R version, it automatically standardizes the data. And it has a very nice built-in program to use cross-validation to find the appropriate value of lambda from all the choice of lambda, meaning you don't have to deal with any of that. In case you're using it, I just want to point out that GMT will actually give you a much more complicated penalty. It'll look at your loss function plus a certain amount of L2 loss plus a certain amount of L1 loss. Okay? So this parameter alpha is a parameter in the function, and depending on how you set it, alpha equal to 0 gives ridge, and alpha equal 1 gives lasso. And alpha is always in the function between 0 and 1, but it gives you an extra hyperparameter you can deal with. In the interest of time, I'm going to skip LARS. LARS is least angle regression. It's a third technique. It has some interesting features, but I don't think it's been used that much. Let's see, one more slides. Okay, so let me very briefly talk about PCA, and we'll talk more about this next week and the week after. But just as a first introduction, there's an important theorem in linear algebra called the singular value decomposition. And what it really says is if you take a matrix, any matrix X, you can write it in this very special form, U times D times V transpose, and U and V are orthonormal matrices. That means all the columns are uncorrelated. You know, they all have all the columns dot product with other columns to be 0, and the dot product of a column with itself is to 1. So what this amounts to saying is that these are bases of unit vectors that are really perpendicular to each other. And then D, the term in the middle, is the important one. That's an n by p matrix. Oops, sorry. I want to move this. Okay. It's an n by p diagonal matrix. Now, what do you mean by a matrix diagonal if it's not square? What I mean is it only has, starting from the top left, you can sort of find a diagonal. It may end too soon, but there is one. So, for example, in this matrix here, I have 1, 0, 0, 0, minus 2, 0. This is a diagonal matrix in the generalized sense. The diagonal elements are 1 and minus 2. Now, this is a nice piece of mathematics. And when you apply this to the correlation matrix, you get what's called principal component analysis. So without doing the mathematics, if you apply the singular value decomposition to a correlation matrix, it says that you can, whatever your predictors were, your P predictors, you can rewrite them in a different basis. So you take linear combinations of them so that the new variables, you get a new set of P predictors that are uncorrelated with each other. And you can understand which ones have the most variance, okay? So that's what PCA is. And so it's sort of finding a very good basis for your set of predictors. Now, the going from largest to smallest isn't per se that important, but it gives you a way to just standardize the actual matrix you get. Okay, so if you take any data set on which you want to perform ordinary least squares and change your predictors so that you're using this PCA set so that your predictors are uncorrelated, then you can run ordinary least squares, you get the matrix, and you get your coefficients. Okay. Now, what happens if instead of doing regular regression on this basis, and this is special to this basis, but you do ridge with a parameter lambda, then you see you actually are shrinking the coefficients by this factor 1 plus lambda. You can show by algebraic manipulations that when you have this right kind of basis, all ridge is doing is shrinking all the coefficients uniformly towards 0. Okay? And so you got to ask me, what about ridge? And rigid does something similar. So this notation, sorry?
Lasso.
Lasso. It's late for me. Lasso is does something similar. So what happens to the lasso betas in this case? Well, it says you take the absolute value of your coefficient, you subtract off lambda now. And as long as that's greater than 0, you do that. If it becomes 0 or less, you just replace it with 0. And then you get back the sign by multiplying by the sign. So what is it saying? It's saying that when you do lasso, the coefficients shrink, get smaller and smaller. When they actually get to 0, you're done with them. So that's why lasso, algebraically, why lasso actually gets rid of coefficients. As lambda gets bigger and bigger, lambda gets bigger than the absolute value of more of these beta j's, and then more of the coefficients become 0. So that's why when you do lasso, that's another explanation of why when you do lasso, you have coefficients be 0. If I remember correctly, I think I have one more slide. Yep. With apologies to Bugs Bunny.
I have a question.
Okay, great.
What's up, Doc?
What's up, Doc? Not much. What's up with you? Any other questions? That's my best moment.
Professor Adam, I actually posted a question and discussion. I think the RMD file that you posted last week, for some reason, KNet is not working for me. So maybe it's something set up on my side. I posted the error as well. So if you get a chance later on, if you can look at it.
You posted it to the website?
On the discussion board, I think.
Okay, I didn't get a notification. I will take a look. I will deal with that.
Yeah.
I'll find out what it is. So you posted your output and where it crashed and everything?
Yeah, it's giving me an error message, which I posted on the chat.
Look, though, if you tell me quickly, maybe I can answer quickly.
Let me see if I can have. Yeah, it says cannot open connection calls with visible eval read.csv.
Okay, so probably, almost definitely, the problem is that it's looking for a data set that's in a different location on your machine.
All right.
So Tejas, it's on from this session 2, right?
Yes, session 2.
Okay,
yes,
so I'll probably work on this week. So probably we can look at it together, or we can work on it.
Yeah. I think it's probably to do with like more of setup. I think not actually.
I think it's because of the location. What Adam is saying.
Yeah.
I say this as someone who has received that error message significantly large multiple lambda times. So I reached the point where I get it. I just look to my right and say, oh, it's not in the right directory. I think I did. I thought I had made some apologies if I didn't. But it's important that you check and make sure that your working directory is where the data files are.
So Tejas, you probably need to download those CSV files and then repoint the path that Adam has used in the study.
I see.
Okay.
I thought most of the I think I'll check. I thought most of the R code was in like comments, right? Like just for this presentation point, right? No.
Yeah, I mean, and I have R code for this too. I will post. And I actually did take the trouble, that in the R Markdown file to put a picture. There's a certain format, and again, I mean, you have to have the picture in your path, and I do have the picture.
So Adam, one question regarding today's lecture. So Ridge and Lasso are still not robust with respect to correlated variables, right? You have to remove the correlation. You have to get to PCA and then apply Ridge or Lasso.
No, you don't have to. The only reason to do PCA is to have this very nice interpretation of what Ridge and Lasso are doing. You absolutely do not need to do PCA to perform Ridge or Lasso.
No, but I'm asking if there are a lot of correlated variables. Would Lasso, would Ridge will pick up the right variables, like the duplicate variables, and set those to 0, or it can set any? It will not, right? It will not identify that these are duplicate variables, and I need to set this to 0. That will not still happen.
It brings this by 1 plus lambda. Since lambda is always positive, it pushes it towards 0, but it never will make it 0. So here's the difference. Lasso might decide based on, let's suppose for a second that your variables are uncorrelated.
Yeah.
Lasso will decide at some point that the coefficient is too small and get rid of it and stick with the one that had the bigger coefficients if you have highly correlated variables. Ridge will deal with the problem in a different way. It'll just say, the problem with highly correlated variables is the coefficients can vary widely. And you might, for a value say, well, x1 and x2 are essentially the same, but I'm giving x1 a coefficient of 100 and x2 a coefficient of -7.
Right.
And then you change it slightly and it goes 50-20.
Right.
What Ridge will say is, sorry, no coefficient can be bigger or small. Has to have every coefficient has to have absolute value at most 10.
Right.
So it'll force this kind of robust behavior, sort of uncorrelate them sort of in practice in some sense by saying the bad part about correlated is you have this issue of coefficients jumping in size because they're determined small. It's just going to say we're not going to let that happen. It'll keep them both in.
Yeah, I mean, I think also you should see the slide where Adam derive the actual closed formula for the betas. You see what happens there is you can, by increasing the lambda, you can make this x minus lambda, x plus lambda times the identity. You can make that as non-singular as you want, right? So you can get something that's here. So what will happen is that normally what can happen is that this matrix here becomes singular. But if you add this one to it, if you take a sufficiently large lambda, this one will be non-singular. And you can make it as non-singular as you want. You're going to get as large determinant as you want. So you avoid any kind of numerical instability also. So that solution will always exist.
Okay. All right, Avinash, you have any questions? Otherwise, we'll end the session now.
All right. Thank you.
Thanks, everyone. Thanks. Bye.
Thank you. Thank you.
Thank you. Thanks a lot. Good night.
Good night.
Night.